Good day. With this episode, we begin the next section of our course devoted to quantum mechanics. In the first section, we talk about the basis of quantum mechanics. We introduce its main conceptions, wave function and operator algebra, and main two, Schrdinger equation. In the new section, we will apply these conceptions to solve the most important basic problems in quantum mechanics. The current episode is devoted to the particle in the one-dimensional infinite potential well, or as it usually said, particle in the box. What does that mean? That means that particle's potential energy depends on the coordinate in the following form. So you can see that it means that the particle is squeezed between two impenetrable walls and moves freely between them. As in any problem of that kind in quantum mechanics, we begin with the Schrdinger equation, which reads as follows. The simplest way to solve this equation is to divide the space into three zones, three regions. In the second region, the particle moves freely, and at the first and at the third region, the potential is equal to infinity, which means that particle in any case cannot penetrate into this wall, and so the probability of finding the particle in that region is equal to 0, and that means that the wave function is equal to 0 too. So in the second region, the Schrdinger equation takes a more simple form with zero potential. Thus, the wave function at the first and the third region is equal to 0, and the wave function in the second region can be found as a solution of this differential equation with following boundary condition. The wave function should be equal to 0 at the boundary between first and second region to match the joining between these regions, and a wave function at point A should be 0, 2 to match the joining between second and third regions. So the solution of this equation is pretty simple and is just a superposition of cosine and sine functions. So we can write down the solution. Let's apply the first boundary condition to this function. That will give us c of 0 equal to c1. So we see that the first boundary condition imposes the c2 to be 0. What about the second boundary condition? It leads to the following equation, c2 sine. The solution of this trigonometric equation is following. So from this equation, we can find the possible energies of the particles. It equals to follow. So only for that values of the energy, the Schrdinger equation can be solved. That means that only at that energy the particle can be at the stationary state. That is why these states are very important in quantum mechanics, and quantum mechanics mainly deals with them. The wave function of the particle in the box looks like this. Let's plot it. The wave function looks like this. It's just a simple sine function. Moreover, the most important is the state with the minimal energy, which is known as a ground state. One can think that in our example, the ground states corresponding to n equal 0. But If we substitute n equals 0, we indeed will gain the minimal energy, E equals 0. But if we substitute then this energy into the wave function, we will see that the wave function would be identical 0, which means that there is no possibility to find the particle inside the box. So there is no particle in the box. That is why this solution is named trivial. And the ground state corresponds to first non-trivial solution, which is n equal 1. Let's project our problem to a more practical example. Electrons in the atoms can be viewed as the particles in the potential well, though not so simple as we have considered. What happens with the atom in the non-ground state, or as it's usually called, excited state? This atom can spontaneously emit the energy in the form of photon and jump into the state with lower energy. That usually happens in the X-rays generators. However, when the atom has reached the ground state, there is no any way down, and it would endure in that state infinitely if there is no external perturbation. That's what happens with all our atoms and molecules. They are usually stable. Let's analyze our energy spectrum in details. First of all, as we understand, in the case of classical mechanics, there is no discrete states, and particle can have any energy while oscillating between the walls. Classical limit in quantum mechanics realizes by taking the limit of zero Planck constant. In our case, it leads to zero energy difference between adjacent energy levels. What are the parameters that can bring us to the classical limit? We can see that in that case, it is a mass. The infinite mass would give the same limit as in case of zero Planck constant. So we can see that that very massive particles tend to obey classical laws, and quantum effects are negligible for them. Another important question is possibility to predict our results qualitatively without solving the Schrdinger equation at all. I can show you that it is possible and pretty simple. Let's write down the Heisenberg inequality. Delta uncertainty in the coordinate of particle is equal to the width of our well. That brings us to the following form of the Heisenberg inequality. Then we can calculate the kinetic energy, which corresponds to the following uncertainty in the momentum. Comparing this equation with the exact energy spectrum, we can see that we quote the main property of the energy, inverse square dependence on the well width and inverse dependence on the particle mass. Thus, we can see that the Heisenberg inequality is a powerful tool for qualitative estimation of the quantum effects, especially when the potential is much more sophisticated and Schrdinger equation cannot be solved. So, in that episode, we saw that the particle state is provided by the Schrdinger equation solution. The latter also gives all possible particles' energy values, or as it usually said, energy spectrum of the system. In case of confining potential, the energy spectrum is discrete. Only certain energy values can occur. The case of non-confining potential will be discussed in the next episode.